the magic happened. Okay, my name is Ronny Salberg. I work, maybe, does it echo as much now? Well, maybe better. I work with the Linux Technology Center for IBM. I belong to the Samba team, and my main responsibilities there are working on a component called ctdb. That's called the clustered TDB database. Why do we need a cluster service when we already have pacemaker? Hands up everyone that has experience with pacemaker and knows what it is. Hands up everyone that knows what ctdb is. Okay. ctdb is different, and we didn't develop it just because, well, let's invent something redundant and new. There were some very good reasons why we did not use pacemaker and why we needed to build something new ourselves. So this presentation will go through some of those reasons to try to explain why was it not a stupid idea to invent something new? Why didn't we use something that already existed? First of all, the problems that we wanted to do was we wanted to build really big and really highly available file servers. Who here runs a file server with CIFS and NFS? It's highly available? No? It's very expensive. Who runs a file server that is used in the traditional active-passive failover mode, where you have two pieces of hardware, one active node? When that dies, hopefully, if you're really lucky, the other one takes over. You do that. Your vendor, you bought it from a NAS vendor. You built it yourself. You do the tests once every month to verify that the failover actually works, right? On your production system that is business critical, right? Nah, no one does that. Okay, but what we wanted was, well, we wanted to sell hardware. But in order to do that, we wanted to build a really big and really highly available and fast Samba server. And how big is big? Well, 10,000 disks, 20,000 disks, big. How fast is fast? Let's say, I hope that we will soon get 100 gigabit Ethernet, because 10 gigabit Ethernet is pretty slow. You can't really do much with that kind of low throughput to your file server. Well, maybe if you're streaming a couple of ISOs at home, it works, but if you are streaming ginormous amounts of data across your data center and you have 50,000 disks that wants to feed I/O on your network, 10 gigabit Ethernet becomes a bottleneck real quick. So you need many of them, many of them. What happened now? Ah, stupid. Consumer electronics. Come on. One more try. Yes?
Wait for it to pick up.
Wait.
Yeah.
No.
Can you try turning it off and back on again?
I tried again. I pressed the right arrow. Okay, let's try it again. Now I press the down arrow.
I've got a Windows box that works.
Okay, let's see. We try it again. What? Oh, cool. Can this actually be happening? Both of them active at the same time. But mouse is dead.
No, mouse is on the screen. Mouse is on the other screen.
Okay, this works.
Yay.
Yeah. So we wanted a big clustered Samba server. We wanted very high massive throughput. We're talking about, well, I can't say numbers, but well, think about these gigabit and 10 gigabit Ethernet cables as very, very slow. And if you want to keep a large number of them saturated from the same file server out to your network at once, even a single piece of PC hardware, no matter how big it is not sufficient, because sooner or later the bus system in your computer is only so fast, memory access is only so fast. So we wanted something that could scale out across many different nodes, and they would all be active and all run at the same time. So instead of having this, one guy runs, the other guy sits and sleeps, we want something where everyone is running, hosting and serving and doing I/O to the same data, to the same disks simultaneously. And it had to be really, really fast. We call that an all-active cluster. We don't have any failover at all. The services are always running, everything is running on your 2 nodes, your 5 nodes, or maybe you have 100 nodes if you really need a ginormous bandwidth. We use it to build really big servers. I think you can find, if you go to the spec benchmarks for the fastest CIFS server ever on the SpecFS site, you can find some information. We also wanted positive scaling. It's very easy to build a cluster that has negative scaling. When you build with more and more nodes, you have to synchronize the stuff so things go slower and slower. We solve that by not synchronizing anything at all. Instead, well, if things gets lost, you get, well, some changes get lost or missing, a node crashes, and you didn't replicate the data. If you manage to detect that and repair it before any client or any application was able to notice that the data went missing, did the data actually disappear in the first place? Yeah, sorry. Yeah. Go away. The data I'm talking about now is obviously not data from the file system or the customer data, but for example the kind of metadata you have inside the server application. If you take for example Samba is running. Inside Samba, in memory, you have lots of data structures to keep track of which files are open, is there a no lock on a file, is there a lock on a file, so if someone else comes in and tries to access the same file, that Samba would know, oh no, you can't read it because it's locked by a different process. All that metadata we needed to distribute across the cluster, so if you had 2 nodes, if you had, but for fuck's sake. If I don't answer, it means I'm not going to answer at all. There should be. So if you had 2 nodes, if you had 10 nodes, still you ran Samba on each one of the nodes, but as far as Samba is concerned and as far as your environment is concerned, you're only running one single instance of Samba. There might be many processes running across 10, 20, 100 nodes, but they all act, everything is coherent, even the internal memory of Samba, to keep it running as...
That was me, sorry.
So that's pretty tricky because there is a lot of internal server state that you need to keep coherent across the processes of them. So it's not entirely trivial, but we do that with ctdb and some pretty huge changes inside Samba. We hope that we will be able to do the same kind of changes in other applications as well, so you get the fully clusterized service. Well, because there are many benefits, many things. It's very hard to do, but many things are very much better and nicer than having active passive if you can clusterize it. For the back-end file system, we use a proprietary cluster file system called GPFS in our product, just for storing the file data. ctdb and Samba, we only manage and synchronize the metadata, or the internal server state. But underneath it all, we still need a cluster file system. And in our product, we use GPFS. It's a very popular file system for high-end HPC applications. We use it Here there is a number of open source cluster file systems as well. They work with varying degrees of success, but some of them work really well. I don't think you have any open source cluster file systems that have coherent byte range locking or with high performance at least yet. So that's something that communities need to work on. At this stage, when we started this project many years ago, nothing existed in the marketplace, nothing proprietary, nothing open source, which is why we started it. We need it because it's a great vehicle to generate sales of hardware, and we hope we'll sell a very large amount of hardware with this. What is it? I think we've gone through that. It's a cluster database. It's all active. There's no failover. All nodes are running, doing I/O to the same disks simultaneously. What we call failover is very much different from what you guys normally would call failover. When you say failover, you mean shoot the old node in the head, start the service up and boot the passive node, and well, that one eventually takes over after a few seconds or a few minutes, hopefully. But what we mean with failover, and what I mean in the rest of the presentation here, is no restart or failing over of services whatsoever. Our kind of failover is pretty much just move an IP address from this hardware onto that hardware. Nothing else. All the services are still running. With ctdb, we also have a plugin interface. It's shell scripts, which allows you to write your own extensions to manage new services with ctdb. Most of the time, you can do it for trivial services like the CLAM antivirus stuff. You can do it just using the shell script to start, stop, and monitor or check if the service is running. We have reasonably good documentation on how to do that, and lots of people have done that. We also have a library called libctdb that allows applications to actually access, read and write data in this cluster coherent database. That is for high level of integration like Samba, where you absolutely need to have all this state coherent across the cluster. Oh, something happened with this guy. 8 minutes to go. We also have via ctdb, since it's already distributing data across the cluster, an API where applications, today it's only Samba, can use special message ports and use ctdb to pass messages from one server process running on one node and deliver a message to a server process on a different node. For example, for Samba, you might have a process 55 running on node 5 has noticed in the database that a record for there is a byte range lock or there's an OOP lock held for a particular file, and it's held by a Samba process on a different node. Maybe Samba wants to send a message over to that other node and check, is that Samba process running, or can I ask that Samba process to yield the lock? We are very happy to have noticed that we have linear scaling on this database for the most common workloads. Linear scaling means that when you double the size, the number of nodes, the total throughput through your cluster also doubles. It's a very nice property with a clustered database. Normally you have negative scalings. When you go from 10 nodes to 20 nodes, well, you get very poor performance. All active have some very important benefits for us, because we build really huge servers. If you run a data center for a large bank, it's very common that you might have lots of these active passive clusters or pairs of nodes. It's not uncommon that in a big data center you might have 100, 200, 300 active passive pairs, each serving a small amount of data. In those situations, well, you want it to be reliable, but if one entire pair goes down, it's not a big deal because the 299 other ones are still running. That doesn't really apply for us. We only have one single cluster that replaces these 300 nodes. We want the cluster to be reliable and always be available. We want our failover to be very, very fast. And we don't want to waste resources. When you have these active-passive pairs, normally you have an active node and a passive node. The passive node is only booted once every 2 years to just check if it still works. But you buy twice as much hardware as you actually need. 50% of your investment in hardware is pretty much never used in active-passive. In all active, it's different. Even if you only have 2 nodes, why should you have one node? You paid money for it. Why should it be powered off all the time? Let it run. Maybe it can help share the workload and improve performance a little bit. And scaling. Some failover modes are very nice in all active, since all active is using a clustered file system in the backend. Some failover modes are incredibly nasty in active-passive failover. If we have here, 2-node cluster, the normal active-passive cluster. Most of the time, one of the nodes is running, the other one is off or is passive, and well, you have one node running, everything is A-OK. Those are those 2 points with OK. When you do failovers, most of the time you want the failover to happen that you go from one OK to the other OK. One node goes down, the other one comes back. In most implementations, you actually go past that one, data unavailable, DU box. You shoot the old node in the head, it goes down. 2 minutes later, the new node comes up and you're back at OK. But that is the one you want to go. What happens in the question mark? Can that one happen in active-passive? Has it happened to your active-passive system? Has it, anyone, you had one where it happened? I use a 3-letter acronym for that, TDL. Do you have recent backups? Well, often when that happens, when both node becomes active at the same time, total data loss is one thing that comes to mind. That's the time when you go and ask your client, okay, well, I have the engineers working real hard now and try to see what we can do. While we wait for them to come back with the status, tell me a little bit about your backup policy. The guy you talk to then always gets very nervous. That problem doesn't exist at all in all active, since you have a system that is built around the concept that you are doing I/O to the same disk subsystem simultaneously from all the nodes. So it's very nice being able to get to this one, a question mark that means, well, this is where we want to be, the normal state of affairs in all active clustering. Both nodes are doing I/O at the same time, and versus the total data loss that gets people very busy to work with locating tapes. Failover is also very, very fast. Different implementations of active-passive failover usually range, in my experience, between 5-10 seconds for a controlled failover, where you force a failover to the passive node, up to a couple of minutes on some implementations. But I think that's fairly normal. So anything from 5-10 seconds to 1-2 minutes would be fairly average in the industry. Since we don't reboot any system, since we don't restart any services. Everything is already running. We are pretty much limited in controlled failover by the fact that how quickly can you do a move IP? How quickly can you remove an IP address from the NIC on node number 5 and do an IP address add, blah, 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 on node number 7? That operation, if the network is reasonably good, so you have all the ARP messages going across and nothing is lost, usually means that you can do failover on controlled failover of IP addresses in less than a second in almost every case. In most cases, it's way, way less than a second. We're talking a handful of milliseconds. The biggest problem, or what takes most of the time for this kind of failover, is not actually moving the IP address and getting the new node up and running. It's actually waiting for the client. The client has a TCP connection. How long does it take for the client to notice that there was a failover? How long does it take for the client to detect that there was a TCP session error? Maybe the client would sit in a TCP retransmit a timeout handler waiting for an acknowledged packet, which would take 1, 2, 4, 8 seconds. For that, we have a small trick. It's not vital for failover, but we have something we call TCP tickles, because if we can do the failovers in like 10 milliseconds, why should we let the TCP stack in the client ruining the failover for us and make it take like 4 seconds? 4 seconds is way, that's an eternity. The way that works is that in the cluster database, we keep track of the identifiers for every single TCP connection in the cluster. So when we move an IP address from node 5 to node 7, and that obviously means that the TCP connection is torn down because we can't move the TCP connection across. On a node 7, what we do is that, since we know that, this IP address has a TCP connection from that client, and these are the port numbers, we then, immediately after we have assigned the IP address to the node, we spoof and send a fake TCP packet back to the client on the same sockets or on the same TCP ports. But the TCP connection doesn't exist on this node. But we send a fake one. What does the client do when it receives a fake TCP packet? Not yet. If it receives a TCP packet for something that looks exactly like that established socket, but the TCP sequence number is all wrong. Not really. If you receive...
Send a reset.
Not a reset, because the client thinks that the TCP connection exists, but it says, the sequence number is all wrong. You're completely out there. What does TCP do then? Yeah, immediately it sends back an empty TCP acknowledge packet to just say, hey, this is the sequence number you should be using. So that's a trick we use to trigger that. Immediately we send a spoofed packet to the client. The client then detects, this is all wrong. The sequence number doesn't make sense at all. I'll ignore the packet, but I'll also send a TCP acknowledge back immediately to just tell him that this is the real number. When we receive this on the node, there is no matching TCP connection established in the kernel. What does the kernel do when it receives this packet immediately from the client and there's no TCP connection matching? Then the node sends a reset back to the client. The client receives the reset. It immediately tears down the connection and the socket becomes readable. Samba immediately detects that, something happened. No matter what it was sitting, waiting for whatever the TCP retransmit to complete, we shortcut the TCP retransmit and immediately get the client to reconnect with TCP. A very, very, very neat trick. It's not Okay, get the battery out. It's my wife's phone. I don't use phones. I don't like phones. It's better when I can call people, but they can't call me. Okay, well, I think we're about out of time, but what I do hope I managed to talk about was at least some of the reasons why we want to do something differently from pacemaker. We want not failover from one server to another. We want scaling. We want all servers to be active at the same time. And as a side effect, we get the high availability part. I guess again. Okay, thanks guys.
Thank you.